Hi, welcome to Chapter 3, Thermochemistry, Overview Part 1, where we're going to cover sections 5.1 to 5.4. So before we really dive in, there's a couple important terms that we're going to use. It's important that you understand their definitions. The first one is temperature. Temperature is just a random movement of particles. Not to be confused with heat, which is really the transfer of energy between two objects due to a temperature difference. And the variable that we use to represent heat is this lowercase q. Work is a force over a distance, and we use a lowercase w to represent work. Energy is the ability to do work or to transfer heat. Internal energy is just the sum of all the kinetic, which is the energy of motion, and potential energies of all the components of the system. The variable we use to represent internal energy is capital E. And the first law of thermodynamics basically says energy is conserved. You can transfer it from one form to another, but you cannot create or destroy it. So let's talk about chemical energy, because that's what we're going to mainly focus on. And it's mainly potential energy that is due to the electrostatic either attraction or repulsion of the particles. So the electrostatic potential energy is defined by this equation right here, where K is a constant, which I gave you right here. It's 8.9 times 10 to the 9 joules times meter divided by coulomb squared. And this Q1 and Q2 are the charges of the particles. And your particles are either going to be protons or electrons. And they have the same charge, but just different size. The electron is a negative 1.6 times 10 to the 19 coulombs. And a proton is a positive 1.6 times 10 to the negative 19 coulombs. And the total unit for energy is what we call the joule, and we represent that with a J. If you look at this diagram right here, if you have two particles that have the same charges, so let's just say we have two protons, and we are bringing them close together, they're going to repel each other. So in order to keep them close together, we have to add energy to force them to be close together. Since we are adding energy, the energy value here is positive because energy is being put in. Say we have a proton and an electron, they are attracted to each other. So as they get close to each other, they're going to want to come together. And when they come together, they're going to release energy. And when you release energy, that is represented with a negative sign. So we could use this to kind of explain ionic bonding. In ionic bonding, you have ions that are attracted to each other. They are oppositely charged, and they are attracted to each other. So you have an electrostatic attraction, and it's seen between opposite charged ions. Energy is released when your chemical bonds are formed. When they come together, when they're forming bonds, so here we're forming bonds, you're going to release energy. And the sign of that is negative, releasing energy. Okay? But energy is consumed when chemical bonds are broken. So over here I'm trying to separate, so I have to put energy in, so it's becoming more positive. That's why this is coming up. So this is an important concept that sometimes kids get confused. When you break bonds, you put energy in. When you form bonds, you release energy. So think about it. Anytime you want to break something, you have to like pull and tug on it. You gotta put some force into it, right? So that's what. Same thing with a bond. If you want to break a bond, you have to put energy in to break it. But if you want to form a bond, you're going to release energy. And it's kind of, you might have experienced this. Anytime you dissolve an ion, well, for most ionic salts, when you dissolve them, the beaker will feel cold. And it feels cold because it's taking energy from your hand, putting it into the system to break apart the ions, because heat has to go in. Heat goes in to the system. And if you remember correctly, this is called endothermic, which we're going to get to in a little bit. So on the previous slide, I mentioned something about a system. So we have to make a good definition of what a system and the surroundings are. The system is what you're interested in. In our case, the system is going to be our chemical reactions, our reactants, and products. Most of the time are going to be our system. So in this diagram here, what you see here, the hydrogen and the oxygen molecules are our system. Okay, the surroundings is everything else in the universe. Okay, so the surroundings are the container, the piston moving up and down. Everything else is the surroundings. The system is just the molecules inside. And our system could be one of three types. There's something called an open system, which I like to think about like a pot on a stove boiling without a lid on it. Okay, it's an open system, so heat can leave. You can lose heat, or you could put heat in. So that's what this diagram is showing you here. Heat can go in or out. Since there is no lid on it, the water can leave, so matter can leave. So you could lose matter, you could lose heat, or you could gain heat, or you could gain matter if, I don't know, somebody poured more water in. Work can be done on the surroundings, or work can be done on the system, and that's what this is showing here. So your open system, everything can happen. It's open. In your closed system, it's like putting a lid on the pot. When you put a lid on the pot, and here's our lid, and this lid is not fixed. It can move up and down. So since the lid can move up and down, this system can do work or have work done on it. Heat can still come into the system. So say you have your pot on the stove, it's still going to heat up from the flame. Or it can leave the system. Like if you touch the outside of the pot, you'll feel it's hot, so the heat is leaving. But matter cannot leave. So you have the lid on, the water is going to stay in the pot. And the third type is an isolated system. Think of this as your thermos. Okay, no work done. This lid is fixed. It's not going to move up and down. No heat can get in because it's insulated. No heat can get out because it's insulated. And your beverage or whatever's inside your thermos is going to stay there. So your matter will not change. And that's an isolated system. So I've been using these words work and heat. So let's really dive into what they are. Work is energy used to move an object over some distance. And you can calculate it by the force you apply times the distance it travels. Okay, so in order for work to be done, it has to move a certain distance. Now, work can go in two different directions. So here is my system. And we just, on the previous slide, we decided to define three different types of systems, right? So here's my system. If my system was a piston, like in the previous one, okay, and the piston moves up, so this moves up, that means work is being done on the surroundings. So in this case, you see here, work is pushing out and it's being done on the surroundings. So when work is done on the surroundings, we represent that with a negative W. It is negative. So when the piston moves up, work is negative. Okay? Because it's being done on the surroundings. In the opposite case, I have my piston again that can move. But this time it's going to, the piston is moving down. So when the piston moves down, work is being done on the system. So that means that work is positive. Work done on the system is positive. Think of it as a balloon, and you're squishing it. Okay? You're squishing it, so you're putting work into the balloon, and that is considered positive work. Okay? But then think of the balloon expanding. Then the balloon is pushing out onto the surroundings, so that is when work is being done on the surroundings, and that is negative work. Heat can flow in and out of a system also. So when heat leaves a system, so heat flows out of the system, we call that negative heat. So here heat is leaving, and this would be negative Q. Remember, Q is for heat. But if I put heat into a system, then putting it in, that is positive Q. Heat is going in. So anytime anything's going in, notice the arrow's going in, that's positive. And anything is leaving your system, that is negative. So changes in internal energy. By definition, the change in the internal energy is just the final energy minus your initial. This symbol here, this capital delta, means change. So anytime you see that, that is going to mean change. And you always, when you're changing something, you take the final minus the initial. That is just a standard way to calculate deltas, okay? So if you look at the first example over here, my initial energy is higher than my final energy. So when I do final minus initial, I am going to get a delta E that is negative because I ended at a lower energy than I started. And where did that energy go? It was lost to the surroundings. So it's leaving. Okay. The opposite, my final state, is ending higher than my initial state. So in order for it to change, I had to put energy in. Okay, so energy is being put into the system from the surroundings. So in this case, delta E would be positive. So when energy is exchanged between the system and the surroundings, it's either being exchanged as heat or work. It could be any ratio of the two. So therefore, the equation for the change in internal energy is your heat, which is Q, plus work, which is W. So if Q and W are positive, your delta E is going to be positive. But if Q and W are negative, then your delta E would be negative. So let's try this example. So you have two gases, A and B, and they're in a cylinder and piston arrangement. So A is a gas plus B is a gas, and they are going to form C, which is a solid. So let's draw my piston. Okay, so there's my piston. It says as the reaction occurs, the system loses heat. So remember, heat is Q, and it's losing heat. So if it's losing heat, it's negative because it's leaving the system. So Q is leaving. When Q is leaving, it is negative. The piston is going to move down. So that means work is being done on the system. And when anything goes into the system, it is positive. So that means my work is going to be positive 480 joules. What is the internal energy change? So remember, delta E is Q plus W. So negative 1,150 joules plus 480 joules will give you negative 670 joules. And that is your change in internal energy. So let's just reinforce this a little bit more. When you are exchanging heat between a system and a surrounding, okay? So when the heat is coming into the system from the surroundings, so absorbed by the system from the surroundings, that is called endothermic. It's going into the system. And that is considered positive, endothermic, okay? When heat is being released by the system into the surroundings, so leaving, heat is leaving, that is exothermic, and that is considered negative, okay? So if you touched your beaker in the first example here, this feels cold. If you touch the beaker in this system, this feels hot. This feels hot because heat is leaving the system, and where is it going to? Your hand. This feels cold because heat is going from your hand into the system. So in order to kind of understand these calculations and these equations a little bit better, we have something called state functions. State functions are independent of the path they took. Okay, I'm going to say that again. A state function is independent of the path by which it took. So in our case for change in internal energy, it is a state function. All we need to know is the energy at the beginning and the energy at the end. I don't care what path it took. As long as I know the initial energy and the final energy, I can calculate delta E. So here's an example here. In order to get to 50 grams of water at 25 degrees C, it could have been ice that warmed up, or it could have been hot water that cooled down. In the end, it doesn't matter. The energy that is in here will be the same, no matter which path it took to get here. So that is independent, and that's called a state function. And most of the time, your state functions are going to be represented with capital letters. Notice how E is capital here? Okay? But heat and work are lowercase, and they are not state functions because they depend on the path. They depend on if you're going in and out, or if you look over here at this diagram, this is my change in energy, this distance here. And there are multiple ways I could get that change in energy. I could have this much heat or this much work, or vice versa. I could have this much heat and this much work. Or I could have all heat. But in the end, the change in energy is the same. So because these heat and work could be different amounts, that they are not state functions. Their path is important. But if you're just interested in the change in energy, then you just need to know the initial and final state. So to help illustrate this, and it describes it like this in your book too. You are climbing a mountain. So here you are climbing the mountain, taking this path. And you finally get to this part of the mountain. You started here. Okay? Which variable is independent of the path you took? So is it your altitude or your distance? Well, what if you decided you were going to be crazy and not take the path and climb straight up like this, okay? Your distance would be different depending on the path. So path A and path B have different distances. So distance is not a state function. Altitude, on the other hand, this is your altitude. And it doesn't matter what path. So altitude, the change in altitude from your initial to your final is independent of the path. So it is a state function. And this is very powerful. Because we have these state functions, we could calculate our change in energy or enthalpy, and we don't have to worry about what path we took. It makes calculating so much easier. So let's talk about enthalpy and what it is. All right, first we have to talk about work. Work is usually if you have an open container, the only work that is done is by the gas either being pushing on the piston or the piston pushing on the gas, right? If you look at this diagram here, the work is going this way. If you look at this diagram here, the work is going that way. This would be negative work, right? And this would be positive work. Kind of understand that better. So you can measure the work done by the gas if you can measure the change in the volume. So your work would be negative the pressure times the change in volume. And most of these processes and most of the processes we do are operating at constant pressure, and that constant pressure is the atmosphere pressure. Atmospheric pressure. Screw that up. Let me just erase that. Atmospheric pressure. And where we live, that is actually 1 atmosphere, right? Is the pressure that we're feeling because we're at sea level. So when your pressure is constant, then the only work that is done is called pressure volume work. And if that is the case, then the heat flowing in and out of our system can be measured as enthalpy. So enthalpy is equal to heat when pressure is constant. So my change in enthalpy will be equal to the heat flowing in and out of my system at constant pressure. And if the process is endothermic, then delta H is positive and heat is flowing in. Right here, heat going in, endo. And if the process is exothermic, delta H is negative, heat is leaving. Heat is leaving, exo. So let's see if we could apply this. Which of the following has a negative delta H and which has a positive? So ice is melting. In order for ice to melt, you have to add heat. So that means heat is going into the system. So delta H would be positive, and this is endothermic. Butane combusts. That means heat is leaving the system. So delta H is negative, and this is exothermic. That's why we burn fuels to heat our houses and all of that, because so much energy is being released as heat. So now let's talk about the enthalpy of a reaction. The change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants. Products minus the enthalpy of the reactants. And just to remind you, at the beginning we talked about breaking and forming bonds. Energy is released when chemical bonds are formed. So you release energy when bonds are formed. And energy is consumed. You have to put energy in to break bonds. So when methane combusts, and this is methane, the energy of your reactants, these are your reactants right here, methane plus oxygen, is higher, notice it's higher up here, than the energy of your products. So when you take the products minus the reactants, you're going to end up with a negative number, or that delta H of the reaction is exothermic, and heat is released. So you will release negative 890 kilojoules of energy. Now, if you're doing the opposite, say you start with carbon dioxide and water, and you want to make methane and oxygen, you have to put this much heat into the system. So again, enthalpy of the reaction is delta H, and this RXN means reaction, or you could call it the heat of the reaction. So here we have hydrogen plus oxygen making water. And the delta H for this reaction is negative 483.6 joules. Okay, so if you look here, your reactants are at a higher energy than your products. And that is why you are releasing energy, and you're releasing this amount. This negative here means releasing energy. If you wanted to write this delta H in the reaction itself, you would have to write it on the side of the products, because that heat is being produced or released. And you would write it as a positive 483.6 kilojoules. Okay, this negative means it's released, and it also means it goes on the product side. So when you write it on the product side, delta H here from the product side is actually negative 483, but you don't put the negative sign here, you write a positive sign. Okay? So the truth about enthalpy. Enthalpy is an extensive property. And if you remember, extensive properties depend on the amount. So the amount of energy you're going to get out of a system depends on how much you start with and how much you end with, the amount of stuff you are reacting. So delta H for the reaction in the forward direction is equal in size but opposite in sign for delta H in the reverse. So say I have A plus B yields C plus 10 kilojoules. So in this case, my delta H is negative 10 kilojoules. If I write the reverse reaction, my delta H here is a positive 10 kilojoules. And your delta H of the reaction depends on the states of your products and reactants. Your states are your solid, liquid, gas, aqueous. These are important. So let's think about this. If I have 2 moles of hydrogen plus 1 mole of oxygen to yield 2 moles of water, and this is the enthalpy of the reaction, how much energy is produced when I am reacting only 1 mole of hydrogen? So I have to use my balanced equation, which tells me 2 moles of hydrogen. 2 moles of hydrogen gives me this much energy. So the answer would be negative 241.8 kilojoules. So this much heat is released. It's exothermic. Likewise, what if I'm given grams? It's just one more extra step. I got to convert my grams to moles. Then I use my balanced equation that says 2 moles of hydrogen will produce a negative 483.6 kilojoules. So when I punch that in the calculator, 3.4 grams will produce negative 407 kilojoules. This negative means that it is released, and it is exothermic. That's it for now.